All right. In our previous video, we went through some of the basics of neutron stars, pulsars. In this video, we're going to delve a little deeper into the physics of what's going on here and the physics of the emitted radiation. Now, this is our canonical picture of a pulsar. There's a lot going on here, a lot of components. And let's spend some time breaking down all the various components. Now, the key component is, of course, the neutron star itself at the center. And it's very massive. It's 1.4 times the mass of our sun, at least. Can be a little bit greater, maybe twice, maybe a little bit more than twice the mass of our sun, in that range. But despite its huge mass, it's been compressed down to a very small size, only about 20 kilometers across. And this compression has all sorts of observational consequences. The first one, perhaps the most important one, is it results in a very, very strong magnetic field. We've measured the magnetic fields of pulsars, and they range from about 10 to the 8 Gauss to 10 to the 12 Gauss. It's 100 million to a trillion Gauss, or Gauss is the unit of measure of a magnetic field. Now, to put that in perspective, our sun's magnetic field is about 1 Gauss. Why the big discrepancy? Well, as you take a magnetic field and compress it, it grows stronger by the square of the compression factor. So we can actually explain these numbers very easily. Let's bring up a calculator. Let's take our sun. Its size is 1.4 times 10 to the 6 kilometers. Imagine compressing it down to 20 kilometers. That's a compression factor of about 70,000. Let's square it. And that's about 5 billion, 5 times 10 to the 9, which is cleanly between 10 to the 8 and 10 to the 12. So these very, very large magnetic fields are pretty easy to explain. Okay. Now, as you can see here, the magnetic field exits one side of the neutron star and enters the other. And these are the magnetic poles. And at the magnetic poles, you get a hot spot. We'll come back and talk more about the hot spot, but this is where the radiation is coming from. Now, if the magnetic field axis is aligned with the rotation axis, this would not pulse. It would simply stream radiation along its rotation axis constantly. And if we're along either of those lines of sight, looking down upon it or looking up upon it, we would see that bright radiation. But if we're looking at it from any other direction, we wouldn't see anything. Now, most of the time, the axes are misaligned. And this is quite common in nature. Take our Earth, for example. The magnetic field axis is not aligned with the rotation axis. There's some separation between them. In fact, the magnetic field axis moves around. Depending upon what's going on down in the core of the Earth, it drifts noticeably from year to year. Anyway, with most neutron stars, the magnetic field axis and the rotation axis are misaligned. The radiation is coming out of the magnetic poles, and so you get the lighthouse model of a pulsar. Those beams of radiation, if they intersect our line of sight, we see pulses, as you're seeing now. And if they don't intersect our line of sight, we don't see the pulses, in which case we don't call it a pulsar. It may be pulsing along some other line of sight, but the term pulsar is an observational definition. So we wouldn't call it a pulsar in that case. It'd still be a neutron star, though. Those by themselves are harder to detect, but sometimes we can do it. Okay, back to this hotspot and the nature of the radiation coming out of this region. Why the hotspot is so hot is still a topic of active research. Different people are working on it, lots of ideas. But it appears to be hot enough to ionize easily. So any particles there, any gas there gets ionized. The electrons get separated from the nuclei. And think back, what happens when you have free electrons in a strong magnetic field? Think back to the case of Jupiter in Module 1C. You get synchrotron radiation. Now, in this case, it's not exactly synchrotron. It's something we call curvature radiation. Basically the same thing, but let me explain the difference. So on the top, we have synchrotron radiation. On the bottom, we have curvature radiation. So the dark line is a magnetic field line. Let's look at the one on the top. You can see the electrons cycling around it. And this gives synchrotron radiation. Whenever you accelerate or decelerate or deflect a charged particle, it emits radiation. In case of synchrotron radiation, a lot of it can often come out in the radio. Now, in the diagram below, same magnetic field line, except the charge is moving along it faster. It's still cycling around, but it has more forward motion than cycling motion. You can see here it's above, here it's below, so it is cycling. But as it moves along the field line itself is curved. So it's being deflected more by the curvature of the field line than by its cycling around the field line. That's the subtle distinction. But it will release radiation just the same. These are two examples of magnetic field-driven radiation, synchrotron and curvature. In the case of pulsars, we're talking about curvature radiation. Now, one additional property of synchrotron radiation, and especially curvature radiation, is it's polarized. So what does that mean? Well, light is a wave, so it travels through space along some plane. This is an example of an up-down oriented light wave. Here's one that's oriented left-right. Here's one that's oriented on some kind of diagonal, etc. Thermal processes don't favor any particular orientation. Some are oriented this way, some this way, some this way. All the different orientations are equally represented. We call that unpolarized light. Now, with magnetic field-driven processes, it is polarized, and the orientation of the polarization is tied to the orientation of the magnetic field. So let's think a little bit more about the orientation of the magnetic field as the pulse sweeps across our field of view. So here's one of the poles. And if you look at the magnetic field lines, they curve one way on one side and the other way on the other side. So I'm in a swivel chair. I'll let my arms be these magnetic fields curving in different directions. And as I sweep by, on the leading edge of the pulse, the magnetic field is curved this way. On the trailing end of the pulse, the magnetic field is curved the other way. So as we go from the front of the pulse to the back of the pulse, the polarization should change. And we're going to look for that. If we can detect polarization and a change in polarization, that really gets to the heart of what's going on here. Here I've painted a picture, but how do we know this is the correct picture? We know it from observations like the observations you took and from the analyses you're about to do, where you can detect polarization and the change in polarization as the pulse sweeps across. Okay, so there's one more part of this diagram that's worth explaining, and that's the pulsar wind nebula. It's pretty cool. So think of the magnetic field. It's coming out of one pole, coming around, going in the other pole. This large structure, the neutron star is kind of small, but the magnetic field is very large. And the farther out you go, the larger it is. But it rotates in lockstep with the neutron star. So close to the neutron star, the magnetic field doesn't have to move very quickly to keep up. But the farther out you go, the faster it has to move to keep up. It's like runners running around a racetrack. Whoever has the outside track has to run faster if they want to keep up with whoever's on the inside track. And if you get far enough out, these neutron stars, as we'll see, are already spinning kind of fast. If you get far enough out, the magnetic field has to travel faster than the speed of light to catch up. And nothing can do that. Nothing can travel faster than the speed of light. So what happens is the magnetic field breaks, and these field lines are what we call open field lines, and they just kind of flail around as the neutron star spins. It's kind of like going in a swimming pool, spinning, but sticking your arms out. That's a source of friction. It will slow you down. You will lose energy. Okay. The most famous example of this is the Crab Nebula. Here's a picture of it taken with the Chandra X-ray Observatory, NASA Observatory. And at the center, you see the neutron star. You see jets coming out of it. That's one way it's losing energy. But it's also losing energy through the Pulsar Wind Nebula. Imagine those now disconnected field lines just wrapping around as the neutron star spins, charges running out along them, and then being released into the Pulsar Wind Nebula. It's a source of friction, a source of energy loss, and as you lose energy, the pulsar will slow down in its rotation. So pulsars all start around a certain speed, but as they slow down due to loss of energy, well, all this turns off. The pulsing stops, the Pulsar Wind Nebula turns off, and it becomes just an ordinary, hard-to-detect neutron star. So the last thing I want to do in this video is just calculate the typical period of ordinary pulsars from stars that just recently died. Okay. So again, neutron stars come from massive stars. Massive stars are young stars. They were just born fairly recently. They haven't had a lot of time to slow down. And the typical period of a massive star is about once per day. Its period is once per day. Now, a star like our sun takes 30 days to rotate. But our sun is not a massive star, so it's been around longer. And the longer you're around, the more you slow down through various mechanisms. But these massive stars that form the neutron stars about once per day, it means their cores are spinning about once per day. Now, the mass that will end up in the neutron star is the mass from the core, and the core is about the size of our sun. So again, it's all about compression factors. In this case, we're conserving angular momentum. As you go from big to small, you speed up, and you speed up by the compression factor. So let's take period of a massive star, 1 day, and divide it by the compression factor. Again, the compression factor is 1.4 times 10 to the 6 kilometers. That's the size of our sun, the size of the core of this massive star. Divide it by 20, because it's going to shrink down to 20 kilometers. And so it will speed up, which means the period will decrease by a factor of 70,000. Let's take 1 day, divide by 70,000. So that's the fraction of a day. It's multiplied by 24 hours and by 60 minutes per hour, 60 seconds per minute, and you get a period of about a second. And indeed, that's what we observe. Pulsars are between a few tenths of a second to a few seconds. And then as they age, they get slower and slower and stop pulsing. And in a special circumstance, they can actually speed up to incredible speeds with very, very tiny periods, much smaller than this, millisecond pulsars. But we'll talk about that in a separate video.